Hello everyone. In this video we are going to have a brief introduction to the digital control, and hopefully you will get enough information in order to do the lab assignment. First of all, we want to see why digital control is needed and it is used. Nowadays most of the control systems are implemented using digital electronics, like the microcomputers, DSPs, ECUs, desktop computers, and so on and so forth. When this happens, the controller becomes a code written in a programming language, such as C or any other programming language in it. Yeah? So instead of having an analog circuit which performs the control action, the control action will be generated using a piece of code, which is written or developed by the user and then transferred to the processor in it. There are several reasons for using the digital controllers, several benefits indeed. When we use the digital control, modifying the program will be much easier than printing a new analog circuit board. If you want to change the controller, you just change the code, while in the case of implementing the controller using analog circuits, you might need to print a new board and implement or prepare the new controller in that way. On the other hand, the cost of a digital hardware is quite low these days, and it's kind of a trend. Digital systems are also virtually immune to electrical noise. So unlike the analog circuits, they are not affected by the electrical noise which is present in the environment. And inserting different kind of functions, such as binary logic, nonlinear operation, is very easier for a computer program than for a circuit. So in general, using the digital controllers makes it easier to implement different controllers and also to modify the controllers and get rid of the effect of the electrical noise. One way to design a digital controller is to design an analog controller, because we know now ways to do this designing. Yeah? You know that you can use the root locus approach, for example, or the frequency response approach to design a controller. PID controller, lead control, lag control, lead lag, and so on and so forth. You can design a controller, an analog controller, and then approximate it by defining a digital controller. Indeed, by finding the discrete equivalent of the analog controller, we can obtain a digital controller. The measured output C of t is measured using an analog sensor usually, or a digital sensor. If an analog sensor is used to measure the output, then we need to convert it into the digital form using A to D converter, because then this signal will be used as the input of the digital controller. Regarding the reference signal for the tasks which are planned a priori, like the industrial manipulator following a trajectory, the reference signal is already defined inside the computer. So we have it in the form of a digital signal. But when it is not the case and a user provides the reference signal, as an example when we have it in the case of active steering in the cars, then it should also be measured and converted into the digital form. So R of t should be generated in a similar way that is done for the C of t. Both of them should be in the digital form. The control variable then will be computed using the controller, using the digital computer, let's say, and then in order to apply it to the actuator, it needs to be converted into the analog form. So a digital to analog converter would be required. And you can see the scheme over here. Yeah? We have the plant, we have the digital computer here, which is the controller basically. This is controller. And then we have these two additional blocks. the A to D analog to digital converter at the input side of the digital the controller, and the digital to analog converter at the output side of the controller. There are two main concepts regarding the digital control: sampling and the quantization. We have seen that the inputs of the digital controller are obtained by using the analog to digital converter. Yeah? It means that they are sampled and quantized. The sampling is given by the fact that C, and also it might apply to R if it's not already available in the digital form. It means that these signals are read at regular time intervals with a spacing which is equal to Ts, and we call that Ts sampling period. So Ts is sampling period, and it means that how often should the signal be measured and provided as the input to the analog to digital converter and eventually to the controller. U of t will be also provided with the same time discretization. So the sampling time will be used at the input side and also at the output side when we want to convert the output of the controller into the analog signal. So basically, sampling means that how often you want to take a sample from the analog signal. In the example which is shown here, the sampling time is equal to 1 second. At the interval of 1 second, the output signal is sampled. It means that it is measured. It's being measured. The quantization, on the other hand, depends on the number of bits used in order to code the signal once it is converted into a digital one. We can have different number of bits in order to represent a signal in the digital form. For example, in the one that we have here, 3 bits are used. In the example here, 3 bits are used. So therefore, with 3 bits, we know that we have 2 to the power of 3, or 8 values could be shown, yeah, starting from 0, 0, 0 up to 1, 1, 1. And therefore, the whole range of that we have for the input signal, for the signal, will be divided into these 8 regions. 0, 1, 2, 3, up to 7. It means that if the value of the signal lies between 0 and 1, which corresponds to a given value, indeed, it will be considered as a single value. If it's in this area, it will be considered as 1. So here we'll have 0, 1, 2, 3, and so on and so forth. So again, in this example, we have 3 bits which are used for coding the signal. We will have 2 to the power of 3 or 8 possible values to be considered. As the number of the bits increases, we will have a more precise reading in it. Yeah? If we have with 2 to the power of 3, which is 8, we have 8 possible values to be considered. If we have, for example, 5 bits, then 2 to the power of 5 or 32 possible values will be considered. And this means that the precision of our reading will be increased. So as the number of the bits increases, our precision will increase. In the following, we will assume that the number of the levels and eventually the number of the bits that we have here are high enough such that we ignore the effects of the quantization. Because if we have a small number of the bits for doing this quantization, then the error that we get in converting the analog to the digital will be considerable. And that's called the effect of the quantization. Now we want to see how we can obtain a discrete equivalent for a PID controller. In order to have the discrete approximation of the controller, we will define a difference equation, which will replace the differential equation associated with the controller, or GC of S. We will use an integer variable k. We'll define a controller that reads E at k times t of S, and remember that t of ts indeed here is the sampling time. And using it plus a number of past values, so like E, the signal error at the time instance k times ts minus ts, E at k times ts minus 2 times ts, and so on and so forth. And we'll also have it for the U signal, U at k ts minus ts and U at k ts minus 2 ts. We'll define the present value of U at k ts, which will be sent to the digital to analog converter in order to apply it to the actuator. Let's see how we can do it for the ideal PID controller. For the ideal PID controller, here we have the transfer function kp plus ki over s plus kd times s times E of s gives us the control signal. In the time domain, we have the expression, as you can see here. So we have kp times E, the proportional part, ki times the integral of the error from 0 to t, which is the integral part, plus kd times E dot, which is the derivative part. And they are considered as up, ui, and ud for the proportional, integral, and the derivative part. Now we will compute the discrete controller term, the discrete control in the expression, term by term. For the proportional one, it will be easy because we know that for up of s is equal to up of t is equal to kp times the error signal. So the discrete equivalent will be similar. Up at k times ts will be equal to kp times the error at the same time instance. Then in order to compute the integral term, ui at k times ts, and we want to obtain it, we have the uit as shown here, ki integral from 0 to t e of tau d tau. We will approximate the integral over one sampling period with a trapezoidal shape. So ui at k times ts will be equal to ki times the integral from 0 till k times ts e tau d tau. So this is indeed obvious. So this comes directly from what we have here by replacing t with k times ts. Now we can divide the integral action into two parts. The first part is ki times the integral from 0 till k ts minus ts, and we add the second part of which is the ki times the integral from k times ts minus ts up to k times ts. So basically the integral that we have here is divided in two parts. But now if we look at the first part here, this is also equal to ui at k times ts minus ts. So we can write it here. We have ui at kts is equal to ui at kts minus ts plus ki plus the second term, integral from k times ts minus ts to k times ts e of tau d of tau. And now we approximate this integral with the expression here. Ki times ts over 2 times e at k times ts plus e at k times ts minus ts. So this is an approximation of the integral term. And it gives us indeed the expression for the ui part, yeah. ui at k times ts is almost equal to ui at k times ts minus ts plus the rest of the expression. Different methods could be used in order to approximate the integral, but we will consider the one that we have seen here, and it's known as the Twistin method, and it's one of the mostly used one, yeah, commonly used ones. We can use the same method in order to find the equivalent digital controller term for the derivative part by reversing the rows of the u and e from the integration to the differentiation, and then we will obtain the expression written here. So ud is the derivative term, ts over 2 times ud at k times ts plus ud at k times ts minus ts is equal to k times the rest of the expression. And then out of that we can find out the expression for ud at k times ts, which is shown here. Now that we have the three terms obtained, we can sum all of these together, and then we will obtain the expression for the digital PID controller, discrete PID controller. So we will obtain u at k times ts at each iteration, and we will store the previous values of the error and ui and ud, and we will also use the present value of the error signal. You should remember that we assume that the computation of the new value of the control variable is made quickly, indeed in a time interval which is negligible compared to t of s, because we need to have this signal, the signal in the control action computed, calculated, and being made available before the next sampling time. So we will assume that u at k times ts is sent to the discrete or digital to analog converter exactly at time k ts. So it is already available at that time. Now we will introduce the concept of z-transform for a difference equation in the discrete domain by simply introducing the term z as the forward shift operator of ts. So you can see the z-transform here. Z-transform of u at k times ts, which is shown by u of z, is equal to the z-transform of u at k times ts plus ts. Indeed, it's not equal, but if we define u of z in this way, we will have these results. So z-transform of u at the time k ts plus ts, so this plus ts will be equal to the z times u of z. If we have it z-transform of u at k ts minus ts, its z-transform will be obtained by multiplying u with z to the power of minus 1. So it's somehow similar to what we had in terms of multiplying the Laplace transform by s or dividing by s, which would give us the derivative or integral action in the time domain. So here, instead of having the integral or derivative action in the time domain, we have the forward or backward shift operator. And then we can use the definition that we just have here to define the z-transform of the integral term. For the integral term, we will have it in this form. So we will have it z to the power of minus 1 times ui plus ki times ts over 2 times the expression which is based on the error signal. And then we can reorganize it and obtain ui as this form uiz is equal to ki times ti over 2 times z plus 1 over z minus 1, which will give us the transfer function indeed for the integral part, integral action. We can have it for the derivative term as well. For the derivative term, it will be in this form. So kd times 2 over s times z minus 1 over z plus 1 times e of z. And the overall transform of the PID controller will be obtained in this way. So u of z will be equal to the expression which is shown here. So this is the transfer function in the discrete domain. Now, if you check this, if you compare this with the transfer function of the PID controller in the Laplace domain, in the continuous domain, you can see that this could be obtained by replacing s with this value, 2 over ts times z minus 1 over z plus 1. And this indeed is something that you can do with any kind of controller as well. You replace s with this value, or if you have the transfer function indeed for the controller in the continuous domain, in the Laplace domain, you just can calculate the transfer function in the discrete domain by replacing s with the value which is shown here. And this could be applied to any kind of controller. Yeah? You can do it for the lead lag controller, for the lag, and so on and so forth. Here we have an example. We want to find the discrete equivalent of the lead compensator, which is described by this transfer function in the continuous domain. The sampling period, Ts, is equal to 1 second. We use the Houston method. Replace s with 2 over ts times z minus 1 over z plus 1, and this will give us the transfer function in the discrete domain, gc tilde equal to 23z minus 21 over 7z minus 5. And then we can convert it into the difference equation. Multiplying the two sides by the numerator by the denominator of each side, we will obtain the equation shown here. And then we know that this z means a shift operator, z or z inverse. And then we can divide both sides by z and convert it back to the time domain. In the time domain, we will have the difference equation like this, and the control action will be provided in this form in the time domain. An important fact regarding the digital controller is regarding the value of the TS, the sampling time. If we choose large values for the sampling period, it means that the signal will be sampled in, let's say, in a long time. So once now, once after 3 seconds, once after 3 seconds, for example, it will take some time, a longer time indeed, for the signal to be sampled. What happens in this case is that we will let the process run without taking correction action indeed. Yeah? So we will create a control action provided to the system, to the actuator, and then only after a while we will do it again. So during this period, indeed, we will do nothing. Yeah? The control action will remain constant. If we have too large value for TS, there will be large delays, which will have similar effects to the additional pause that we had in terms of increasing the overshoot, longer settling time, and eventually it might cause instability. Even though we have, it has substantially different in its nature, yeah, but it will give similar effects. On the other hand, if we make TS too small, it will require high performance, so it will become expensive if you do it quite frequently, and the effect of the quantization will also increase. In this example, you can see that depending on the application, indeed, different values for TS for sampling time could be used. For example, for some applications, TS equal to 500 milliseconds is used for energy efficient building control by Siemens, for example, which is a longer sampling time compared to what we have here, which is 18 nanoseconds, and it's used for the multi-core thermal management at EPFL. So the sampling time would also depend on the application that you want, how fast you want to do the control, or how fast your system is indeed. Yeah, if the system is naturally slow, then bigger sampling time might be already enough. As a rule, to determine the sampling time, we need to stick to the equation here, which follows the Nyquist-Shannon sampling theorem. Omega s, which is equal indeed or defined as 2 pi over Ts, should be bigger than 2 times omega c, where omega c is the crossover or cutoff frequency. Some heuristic rules also are provided here. We need to choose Ts, which corresponds to omega s, choosing omega c where T of j omega is almost equal to L of j omega, and it's almost equal to minus 40 decibel. We choose Ts such that the rise time interval contains about 6 samples. So during the rise time interval, we should have around 6 samples. And also we should choose Ts such that the settling time to 2% contains about 10 to 40 samples. So these are some heuristic indeed rules in choosing the sampling time. Finally, we should also remember that the overall effect of sampling introduces a delay in the system, which will decrease the stability margins as well, yeah, the phase margin. We have seen the effect of the transport delay already. And since doing this sampling will introduce some delay, it means that our phase, some negative phase will be injected to the system, and therefore the phase margin will be decreased. And as a result, when you want to design the analog controller first and then create the digital equivalent, keep in mind that you should pick a bigger value for the phase margin in order for your digital controller not to be unstable due to the effect of the sampling. Alright, so that's all for this video. I hope this explanation will help you in doing your lab assignment on designing the digital controllers. Thank you for watching, and see you in the next video later.